Thank you. Case 1, A is his own team. So here it is. A is one team. Then what can I do for the rest of the design? Then how many teams do I need to assemble now?
Two.
Out of how many people?
Four.
So it says 4, 2. Do you agree? So I'll do the other 2 teams, and then I just join A as its own team, and that's it. I got 3 teams. Yes?
Are the teams specific, so it's like A is part of specifically team 1, or?
No, A is team 1. Him by himself. Nobody else is there.
Oh, I mean like,
Indistinguishable teams.
yeah, indistinguishable
It says
teams, or?
Yes. So there are 3 teams. So A is one of the teams, and then there are no names or anything. So generally, what matters is which persons are on the same team, which persons are teammates. That's the only thing that matters. And that's it. So total count is what? S for 2 for this case. Case 2, A is not alone. So that means A must be with someone else. And that's it. No overlap, no missing cases. What can we do if A is not alone? Here's what we can do. We can design now teams from other players. So in how many ways can I do that? Design 3 teams from other players. How many ways can I do that? S what? How many players are left? How many teams now? All right, once I design that team, what can I do? Decide who will A join. Who can A join? First team or second team or third team. So how many options does A have? 3. So it's 3 times S for 3. Here's the count. But what's the problem? I don't know those. But generally, I hope you understand how this reasoning works. So what is the Stirling formula connection? It says the following. If he is alone, reduce both by 1. If he is not alone, reduce number of players, the same team, he can join any team he wants. Does it make sense? What I just did here is, doesn't matter that these were 5 and 3, works always. What makes this recursion a little tricky to apply is that there are 2 indexes changing. You see N is changing and K is changing. So there is double recursion. And it's a little hard to organize it. So design is not that bad, or memorize it. I very often ask this question, really, because it's interesting for you to develop that practice, how to play with double recursion. So how do we answer the question S5-3? Here it is. First, there are some very easy answers. What would that be? Fact 1. Sn1 is what? It's just 1. Why is that? If I have only one team, how can I make that one team? Everybody's coming, agree? Everybody's on team, and that's it, only one choice. What about Snn? So everybody's his or her own team, so again, only one way to do it. So there's only one design in those extreme cases. Now, I want to do Sn2. And I can already here start doing recursion, but I don't want to. Why? Because we can answer that one quite easily. Why? I can give you the formula for Sn2, and I think I posted on the Blackboard even formula for Sn3. That one's tricky, but Sn2 is very, very easy, but please pay attention. What is Sn2? If I have n people, in how many ways can I separate them into 2 teams? Generally what? Just give me the first team, because second team is just everybody left. In how many ways can I choose a subset of a set? How many subsets does a set have? Two to the n subsets. But I have to intervene on that. Not all the subsets are good. Why? Because teams are non-empty. I cannot choose empty subset, and I cannot choose everybody because there must be a leftover. So actually, it's 2 to the n minus 2. Do you agree? But then I need to divide by 2. Why? Here is an example. If I have 1, 2, 3, 4, is 1 its own subset, yes or no? And so with 1 as a subset, I will have 1, and then 2, 3, 4 are the second team, do you agree? But there is next subset, 2, 3, 4, the design as a leftover what? Is that the same partition or not? But with a double count, that's why we divide by 2. Because two different subsets actually complements define the same partition. That's why we had double count. And then if I, of course, divide by 2, what do I get? 2 to the n minus 1 minus 1. So this is the formula. So what is it? Let me erase this and now play the formula. So here is the way to play this correctly. First, I don't want to start with what I need because it's going to be quite tricky. Let me provide all the 2's that I need. S what? Let me do S72. How much is S72? S62, S52, S42, S32, S22. S22 you know is what? 1. How much is S32? Reduce by 1, raised and subtract 1. So what would that be? 2 squared, which is 2 squared minus 1, which is 3. 2 cubed minus 1, which is 7. 2 to the 4 minus 1, which is 15. 2 to the 5th minus 1, which is 31. 2 to the 6th minus 1, which is 63. Everybody okay with this? So these are 2's. And then, let me go here. Okay, S53 is okay. So let me see. S53, recursion set is what? S what? Reduce both, so what would that be? S42 plus 3 times S43. So what happened? First number I already have in the list, do I? For 2's, S42. For 2 teams, I have all those ready, so that's lucky us. Otherwise, you would need to run another recursion. So how much is first number? 7. It's there. So S42 is 7 plus 3 times. I need S43. And that one I have to open using formula again. It might be a good idea, actually. I didn't know that before I do it first time. Even if they ask me S53, what should I do? Not start from S53. I should start from the bottom. S33, S43, S53. So don't start where they ask you, start from the bottom, because then you will have a result ready instead of opening parentheses. But anyway, can I open S43 using recursion, yes or no? Well, what would it be?
S42.
No.
S32.
S32, reduce them both, plus what? 3 times what? 3. Now everything is ready. So it's 7 plus 3 times S32 is here, which is 3, plus 3 times 1, and that's it. This is 25. I think so. 3 and 3 is 6 times 3 is 18, and 7 is 25. Here it is. So 5 persons, if you want to separate them into 3 teams, You can do it in 25 different ways. So this is a nice formula. First, because it solves nicely combinatorial problem. The other one, it's interesting how you need to play both indexes. Sometimes k goes down, sometimes n goes down, but at the end you will finish it because the sum of those is always lower and lower. So induction on n plus k tells you at the end you will reach levels. Because here the sum is n plus k, here n plus k minus 2, n plus k minus 1. So right objects are simpler than the left one. So there's a proof that at the end everything will collapse to trivial values. All right, so supposedly you see a little heavier problem solving today, just all kinds of different configurations. They all have the same leading ideas, but technology is different. Again, next one is also interesting, and that one is, it's a famous problem. All right, just on the board, since I calculated S5.3, what if I need S6.3? Can I do that now quickly, yes or no? Because I need just that S5.3 and S5.2, and generally you can get 90 and so on. All right, next problem, example 517. Nice combinatorial problem that says a single line divides plane into two regions. Let Pn be the maximal number of regions into which n lines divide the plane. Find the formula for Pn. So one line, n equals 1. Two regions, so P1 is 2. What about n equals 2? If you have two lines, what's the most regions you can get? 4 regions. 1, 2, 3, 4. So P2 is 4. Does it look like doubling all the time? I don't know. How about P3? So here are 2, and then it's not going to be doubling. Why? Because I'll have a problem here intersecting everybody. I cannot intersect all 4 at the same time. Do you agree? The most I can do 3. How about this? Is this good? So what happened? The only one that I didn't split is this one. This one was split, this one was split, this one was split. So P3 is what? 7. So how much is P10? That's the question. Looks like a very hard problem, don't you agree? Because how do you control, who can you intersect, who you cannot. Because there are tons of regions. But let's analyze what happens, and that will give us actually a recursive formula immediately. Let me erase this for a moment. When you split the region, actually, what are you doing when you split the region? You are hitting the border. Because you must hit the border of that region to enter, that's continuity, like intermediate value theorem. If you want to enter the region, you need to hit the border of that region. Do you agree? So what then? To enter the region, you must hit one of the lines. Can you hit a line with my new line now when I make it? It has to hit first line, it has to hit second line. Do you agree? Hits them both. What now? If someone wants to get a new region, don't think of regions, think of lines. So what's the most lines? So here it is. Let me see if how many lines, can I hit all 3 lines? Yes or no? Yes. And then what happens? So when I hit, so let me this be. How many regions did I split? 4. Why? Because here it is. You can say the following. Every time I want to split the region, I have to enter. Do you agree? How do you enter that region? By hitting one of the lines. And you can never hit a line twice. Do you agree? Because two different lines can have at most 1 point together. So, I hit one, so this is the first time I hit line number 1, I build new region. Here it is. Here is that new region. Then to split another region, I have to split the second line. Do you agree? Oh no, I split the second time, so third time. So here are the stars when I hit the lines. Whenever you hit the line, then you split the region. Whenever you hit the line, you split the region. So you actually what? Add every time exactly as many lines that you hit. So that would be what? Pn plus 1 would be Pn plus, looks like n, or maybe, I forgot something. What is it?
Is the P sub 3 7 the sub 3, is that how many lines?
Yes, exactly. But there was something else. Look, I said the following. So I'm counting when I enter the region. So I said, to enter the region, you have to hit the border. So to split this region, I had to hit this border. To split this region, I had to split. So hit the border and get into region. But there is one that doesn't need that. Who's that? The first one. First one just comes from forever. So Pn plus n plus what? 1. By the way, if you miss that by 1 or something, your initial cases will give you the control. So what this says is what? P1 is what? How much was P1? P1 was 2. 2. So if I use my formula correctly, P2 is 2 plus 2 plus 1. No, n is 1. So 2 plus 1 plus 1, which is 4. How much is P3? Is P2 plus 3, because this and this is the same number. So that would be 4 plus 3, which is 7. How about P4? Just take your Pn and add your index. So take this and add this. 7 plus 4, 11. 4?
2 plus 1 plus 4.
N is 1 here.
Oh,
That's P2.
that's n plus 1. Okay.
Yeah. And that's why I changed my strategy. I said, since this is n plus 1, so just read your index. Whatever your index is, that's the number you add to the previous one, and so on, and we can get it. What interesting thing is, this is a recursive formula. Can we get explicit formula for this, for P10, so that I don't go step by step? The answer is yes. Again, we'll do it next week. So we'll learn how to solve those like differential equations to get, it's not always possible, but sometimes it is. Do you have a question? Yeah.
I was just curious if it's like the summation notation. Could we shift it? Could we have like P of n equals Pn minus 1 plus n?
Of course. No, then if you shift it, it will be like this. Pn equals Pn minus 1 plus n. If you prefer that way, yeah. So you say current and his predecessor, or here I say me and my followers. So just perspective, the same thing. It might be even better, because then you have these two numbers are the same instead of looks maybe better. Depends. Sometimes people like this, sometimes this, yeah.
Is P1 just what we set it as at 2, or is it just P0 1?
No, P1 is 2. Why? Because if you have one line, then you have two regions, left and right. So one line splits into two regions, that's obvious, and then you keep going. Any comments?
When you have P sub 3 equals 7, it seems like you end up getting 8 different planes.
No, 7. 7, I added fourth line later on, forget this. So here are those 7 regions.
Oh, that's right.
1, 2, 3, 4, 5, 6, 7. That's good. All right. Let's now revisit two simplest cases and most popular. I left them for the end because they are just little stories and need less concentration. So probably where I would concentrate the most, this is Stirling numbers, make it sure that you can do that always. And also this one with the digits repeating, non-repeating, that's a huge thing. So generally this repeating or 1, 1 repeating, non-repeating, you'll see that very often on the exams where you cannot call formulas, you have to do the design. And I think that that's very valuable. And then two historically famous problems, and I'll mostly just go and discuss them from the screen. First one is example 512, which is Tower of Hanoi. Have you heard about that problem? Many times. So what happens there? Solution there is surprisingly simple once you think of the recursion, otherwise looks very hard. So what is Tower of Hanoi story? It's called Providence traditional. That's what it's called. So 512, Tower of Hanoi. So what is the story? We have 3 poles, and we have n rings. N rings of different size. And they are all lined up here on one of the poles. So here are the rings, let's say 5 rings. So here's the rule. You want to move these 5 rings from pole 1 to pole number 3. The question is, can you do it, but without ever placing bigger ring on top of the small one, like it will break it, it's too heavy, so it'll do the damage. So can you do it in a legal way following this rule? So can someone recall the argument? Yes.
So you move the first disc to the third, you move the second disc to the second, you move the third disc back onto the second one, and then you kind of keep going.
What? First here.
Yeah, you move the smallest disc to the third one.
Okay.
You move the second smallest to the middle one, and then you move the smallest one back onto the second smallest.
And then?
And then you move the third smallest one onto the empty pole.
Okay.
And then you move the other 2 back onto the third pole.
Okay.
You just kind of keep going.
Okay. And what if I have 20? How would you give me an ironclad proof that could be done?
That's the algorithm.
That's an algorithm, exactly. So generally, the way to make a proof is actually a proof by induction, where you actually do construction by recursion. So I told you, construction by recursion, proof by induction. How do you do that? Here it is. Let's forget. So let's imagine that we can always, so suppose, I'm sorry, I'm starting induction wrongly. Case n equals 1. If I have only 1 ring, can I do it?
Yeah.
Just take it, carefully put it on the other one. Nicely done. Assume we can do Tower of Hanoi with K rings in a legal way, okay? Now, so that's inductive hypothesis. Now we want to prove that we can do it with K plus 1 rings. So here's what we'll do. Take K minus top K rings on top. And move them to pole number 2. Can we do that? That's inductive hypothesis. Because with K rings, I can always do it. But you can say, wait a minute, what about this bottom ring? While I'm doing it, will I ever be in danger in ruining the rule to put bigger on top of smaller? Is this the biggest one, yes or no? So you can disregard it. If you ever need to put anything on it, it will survive it because that's the biggest one on top. So generally the fact, so I can disregard, because you can say, oh, you cannot call inductive hypothesis because that you have that extra ring, but this ring doesn't prevent you from doing any moves. Whatever moves you give me, I'll perform them, and this ring will not ruin your strategy. Do you agree? So what then? So according to inductive hypothesis, we can move top K rings to pole number 2. When that's done, so here is the next picture. So here is the large one, here is the short pile, 3 is empty. What can I do now? Move the bottom one to number 3. So here is the pile, here is empty, here is the bottom one, and then what do I do? Again, do the same procedure, just poles numbers are different. Again, do inductive hypothesis, and that guarantees the proof. As I said, the only thing that ruins your inductive hypothesis is the presence of the bottom one, but that really doesn't matter. And actually, we even have a recursive formula for this procedure. What is the recursive formula saying? So procedure, what? Number of moves at the level k plus 1. What is the number of moves? You do moves for k, you do 1 move plus move for k. Do you agree? Because to do k plus 1, using this strategy, you just move k. So to go from here to here, this is mk moves, whatever that is. Then you do that 1 move, and again mk moves. So I even have recursive formula for the number of steps. It is 2mk plus 1. And again, we will be able to get the explicit formula for this, for the number of steps in this case. Today, we are mostly concerned about design. Even next week, we'll learn explicit formula. That's not the main idea. That's actually just, for easy cases, here is the way to kind of get explicit formula. It's much more important that we learn today how to make this design. All right, so that was Tower of Hanoi story. Does that make sense? Everybody's okay with this?
You're allowed to move them in a chunk?
No, you are not. You are just calling K procedure, whatever that was. So you are not moving them, so whatever was, do this, do this, do that. Just K procedure calls poles. MK procedure is done for the poles 1, 2, 3. Do you agree? And then when I do it here, it's also procedure. I'm calling actually MK132, which is the same procedure. How poles are labeled doesn't matter. Because I don't want them on 3, I want them at 2. Does that matter? Not really. It's hard to imagine that would be a problem. So that's the only thing. And also MK star. Why am I putting star? And not only that, but also there is something that's non-typical from in this situation. Is there an extra ring lying there? Is there a ring there? So you can say, oh, MK didn't know about that ring, but that doesn't matter. So there is little change in the configuration, but that change doesn't influence your moves at all. So this would be a little more precise labeling. All right, the last problem for today to analyze is the famous Fibonacci's problem. So what are the Fibonacci numbers? It's a famous problem from Middle Ages, and the question was surprising, particularly for that level of mathematics at that time, and their kind of awareness of the size of numbers and recursive ideas to actually see a problem like that. The Fibonacci number says, and the question is, how many pairs of rabbits can be produced in a year from a single pair of rabbits, and from a single pair, if rabbits are able to mate at the age of 1 month, so that at the end of its 2nd month, a female can produce another pair of rabbits. So what happens? So here's the story. So how do you make a Fibonacci sequence? How do you make a recursive connection? actually before we make a recursive connection. And that's very often the case. You don't immediately see how are things connected. It's always a good idea, and that's what we'll practice more on Wednesday, to cover a first few basic cases. You will need initial values anyway, and also gives you an idea how they behave. So here it is. How much is A1? I don't know. Did I label it A1 or A0? Sorry, let me just keep it consistent. F0 is 1 and F1 is 1. All right. So, all right. So F0 is 1. What did I record here? I recorded that sentence F0 is 1. What did I record here from the story? From a single pair. So in the beginning, no time elapsed. So we have one pair. Do you agree? 1 month later, F1 is still that single pair. Do you agree? And then what happens? F2 is now, there is a new pair and this old one. So that's how much? 2. But then what happens? After 3 months, who do we have? Those 2 are still alive, do you agree? So whoever's there. But only those that were here in the previous stage will have new offspring. So these are the only ones that will give the offspring. So that will be how many new pairs? 1. So this is what? 3 altogether. 2 that were there and 1 that just came. But now what happens? F4, I have those 3 that were already there. But how many of them can bring new pairs? 2, those that were here month before, 3 plus 2. And then when you look at this, what happens? We see the formula. What is the formula? Formula says actually what? What is this? How did I get that 3 plus 2? This is just F3 plus F2. So generally what? Every member is the sum of the 2 previous members. Do you agree? And that's a famous Fibonacci's recursive formula. So formula says what? So Fibonacci that would be 2 sequence. So F0 is 1, or you can call it F1. Doesn't matter, just shifting index. F1 is 1, and then you have Fn plus 1 equals Fn plus Fn minus 1. And then using this sequence, then you can get, so what is the sequence? 1, 1, 2, 3, 5, 8, 13, 21, and then 34, and 55, and 89, and so on. And then let me read the answer to the problem. So what was the question, by the way? How many pairs can be produced in a year? So generally what? The answer is we want F12, which is what? When we continue, we'll get F12 to be 233, but our answer is 466. Why? Because these are couples, and the question was about number of rabbits. So total number of rabbits at the end of the year will be 466.
So this is a pair of female rabbits?
Whatever technology is. So what? Probably, if we want to make a similar Ebola problem, then it would be much more dramatic and involve bigger numbers. So what? This is one of the most famous Fibonacci sequence, one of the most famous recursive sequences. What is very interesting, and you have a problem like that. It's not so interesting for us as it is a little bit for calculus. There are a couple of very interesting problems toward the end. Look at the quotients here of Fibonacci members. That's very interesting. What are the quotients? 3 halves, which is what? 1.5. So this is 1.5. This is 167. This is 1.6. This is 13.8, which is, I don't know, something like 168 maybe. What happens? All these numbers are a little bit below and a little bit above one number when you take a limit of both sequences. They go like this. There is a certain limit, and those lower go a little 1.5, 1.6 comes closer from below. Those overestimate come closer from up, and they squeeze one number. Golden ratio. And that golden ratio satisfies. What is golden ratio? Do we all know golden ratio? So this is the number that satisfies actually what? The equation x square. What is the golden ratio equation? X squared plus x. No, it's minus 1 plus or minus square root of 5 over 2. So, or 1 plus or minus square root of 5 over 2. Oh, x squared minus x squared plus x minus 1 equals to x squared minus x minus, of course. It's this one, yes. So, because this, you see, we have x squared equals x plus 1, that's an plus 1 equals an plus an minus 1. So when you get like this, your solution is r equals 1 plus or minus square root of 5. If you take 1 plus square root of 5 over 2, that's the golden ratio. And by the way, what's the big story about golden ratio? Couple of little details. Why is that now? Another story, and it's interesting always in mathematics how nicely they converge. That's actually considered the most aesthetic, for ages, as the more aesthetically pleasing rectangle. Why? Because look, is this a rectangle? Yes, but not typical. That is too special, do you agree? What about this one? Do you like this rectangle? Yes, if your dog looks like this. There are some dogs that look like this. But really, people like, and all those frames, usually like this one is something like golden ratio. Aesthetically pleasing is the one, and that's from time of Aristotle. If this is, let's say, A, the short one, then this one is 1 plus root 5 over 2. And that's like 1.6A, and that golden ratio. And it appears very often in interesting situations. So generally, those fractions of consecutive members are approaching exactly golden ratio. So that's another interesting curiosity of this. All right. So we have a plan for Monday. So exam here for everybody, and